Numerical integration refers to an approximation of a definite integral, and we do this using subintervals. So we divide our domain AB into a certain number, we'll say n subintervals, and each of those has a length, we'll call that delta x b minus a over n. If this is looking familiar, it is, because we did this already with L sub n, R sub n, and M sub n. But we don't have to use L, R, and M. We can actually use some other rules. For instance, one of the cool ones that I've mentioned already that we can use is the Trapezoid Rule. And the Trapezoid Rule basically takes your function and from A to B divides it into those little intervals. We'll just do a couple of intervals here, and creates trapezoids. And a trapezoid has two sides parallel and two that aren't parallel. And sometimes those trapezoids might look like rectangles, but it estimates it with these trapezoids. And the formula for this is given as t sub n is equal to 1/2 delta x times, and this is the part that gets a little confusing, but you have to take your first y value, y is 0, which would be this value right here, and you have to add 2 y1s, which would be your next one. You're adding it twice, once for each time that you would get to it, and 2 y2s all the way up to 2 yn minus 1s and a yn at the end. And of course we'll use the letter j. Y sub j is the function being evaluated at a plus j delta x, which is what we saw with r sub n and r sub n and m sub n in the last unit. It turns out that this trapezoid rule is actually pretty good approximation. You can see that it rides the line a lot closer, and it turns out that it's way better than L sub n or R sub n. But it also turns out that it's not as good as you might think, because M sub n is twice as good as T sub n. So if we really had to choose just one to use for a really close approximation, M sub n generally does the best job. It's generally twice as good as T sub n, and T sub n is better than these two, R sub n and L sub n. So let's take a look at some other things with T sub n, like the error. And the error for T sub n can be found by taking the absolute value of the difference between, well, what's the actual minus what did you calculate. So that's also true for R sub n, L sub n, and M sub n. The error is the same calculation. But the max error, or what can be called the error bound, might be a little bit better. That's like how far do we expect it to be off by. And this is the calculation for T sub n and M sub n for the maximum error bound. Formulas the error bound for T sub n and M sub n. Those errors will be what you expect the error to be, will be less than or equal to this equation. And B, A, and N, we've seen those before, so those should be fairly standard to you. But this K sub 2 is a certain special number, and we'll get to that in a second. There's a couple conditions on these error bounds, so let me state those as well. One of those is where the second derivative has to exist and is continuous, and the other one has to do with this K sub 2. We have to find some K sub 2 number. It's any number that we want, but we have to find some K sub 2 number such that the second derivative's absolute value is less than or equal to that K sub 2 for all x's in that interval. And we'll take a look at an example of what that means. I know these formulas are looking pretty complicated and pretty intimidating, but they're actually pretty easy to calculate. So here's an example. We want to calculate t sub 4 on a certain interval of our function dx and calculate the error bound and verify those bounds. So like we did before, we want to calculate delta x first. So 9 minus 1 over 4 is 8 over 4, which is 2. So we then use t sub n, and it's 1/2 delta x y0 and 2y1, etc., all the way up to your n value, and you get 1 y sub 4. And to calculate those y sub zeros, we're finding the endpoints. So we know our delta x. The first endpoint is the function evaluated at 1, so that's 1, and then the function evaluated at 3, which is 2 times root 3, and then the function evaluated at 5, and the function evaluated at 7, and the function evaluated at 9, but don't double that one. So these ones in the middle, they all get doubled, but the other ones don't get doubled, the ones on the ends, with this formula. And so that's about 17.2277 and some more decimal places. And now we can move on to the error bounds. So we can go and calculate the second derivative. So we've got f of x is equal to x to the 1/2. So the first derivative is 1/2 x to the negative 1/2, and the second derivative is negative 1/4 x to the negative 3 over 2. So it exists, and if you take the absolute value of that, we need to find some k value, or k sub 2 value, that is on 1, 9, the interval that is the largest k value that this becomes, or the largest value that this becomes. So let's take a look at that. On the interval 1, 9, the largest that this gets, which is actually 1/4 x to the negative 3 over 2, the largest that this gets, so if I put in a 1, it's 1/4, and if I put in a 9, I get something that is smaller than 1/4. So the largest that this gets on that interval from 1 to 9 is 1/4. So since it is 1/4 that's the biggest that it gets, I just set my k2 to be that largest value. And then I go and calculate my error bounds. And I get 1/4 times 9 minus 1 cubed over 12 times 4 squared, and I get 0.6 repeating. If I go and calculate the actual error, I get the integral from 1 to 9, x 1/2 dx, take away what I calculated, which I have above, t sub 4, and I get about 0.1055 or 5659. And you can see that the actual error is quite a bit less than the error bound. And the error bound was the maximum amount we thought that this was going to be off by. So looks like it verified quite nicely. It turns out t sub n, as I said, t sub n is not a bad way of estimating it. It's better than r sub n and l sub n, and m sub n is even better. But there's another rule. This is not part of APAB, but I thought I would show it to you because it is part of first year calculus generally. There is another rule that's even better, and it is called Simpsons Rule. And Simpsons Rule combines m sub m and t sub n using a weighted average, and it only works for n as even. So you can have n as 2 or n as 4, but you can't have n as 5 and apply Simpsons Rule. And Simpsons Rule is given as s sub n, and it's 1/3 delta x, and then you have your y0, you take 4 y1s, 2 y2s, and you keep doing that, 4, 2, 4, 2, 4, 2, until you get 4 yn minus 3s, and 2 yn minus 2s, and 4 yn minus 1s, and you finally end up with yn as your last term. And you still have the same, delta x is still b minus a over n, and to calculate any of these y's here, you still evaluate the function using a plus j delta x. and it has an error bound that is a little bit more complicated than the ones that we saw before. So the error bound is less than or equal to k sub 4 b minus a to the fifth over 180 n to the fourth, and k to the fourth just refers to the fact that you're taking, instead of the second derivative, you end up taking the fourth derivative of x as absolute value, and you're finding out what the largest k value is on the interval from a to b. If this seems complicated, it is a little bit more, but it's a pretty cool thing when estimating that people came up with weighted estimate or weighted average using m sub n and l sub n. That's even more accurate than just m sub n. This really does get quite accurate to the actual integral. Come to class ready to try out some of these questions.